Okay, so I will start to give a brief introduction before Said will start with his webinar. So today we are very happy to have Said Ouala that will give a webinar today. So this webinar is organized by the SCOR working group for the BGC. That is a working group about the coordination of the development of gridded four-dimensional data products from BGC Argo observations. So sorry, my slide. Okay. This working group has the objective to facilitate discussion and coordination among the different scientific communities around the development, the validation, and the distribution of the 4D BGC products. With a focus on the BGC Argo array. And so the goal is to significantly enhance access and utility of BGC Argo observations through these 4D BGC products, and thus help us to refine our understanding of ocean biogeochemistry and improve models and reanalysis products, and finally inform policy decisions. So you have here a picture of the group that has met during the last Ocean Science meeting in last February. So this group has settled a web page where you can have access to all the BGC, the 4D BGC products based on BGC Argo observations. And we are updating this page with new products. So this page is available from the BGC Argo official website. And you have here an example of all the products that are on this page now. If you come across a new product, you can email us, John or me, and we will have this page set. And we just put the products with some DOI and article reference. Here is the link to the 4DBGC website, where you can find all the information about the group and all the news about the activities and so on. And you can sign up to receive updates on our activities. You can have this link on the website, and through the YouTube channel for DBGC, you will have all the records from the previous webinars. And so today, we thank Said Ouala that will give us a presentation about his method called Neural-BGC, about the emulation of biogeochemical properties from temperature and salinity. And so thank you, and I give you the floor, Said.
All right. Okay, so can you see my screen? And it's in full slide, full presenter mode, right?
Yes, it's perfect. Thank you.
Okay, great. So thank you, Raphael and John, for this very nice introduction, and also for proposing me to give a webinar in this very nice webinar series and very nice group that you have about some of our recent works regarding the neural network emulation of BGC variables. And when we say BGC variables here, we mainly mean dissolved oxygen nutrients from temperature and salinity data. So the model, we called it Neural-BGC, and it's used, and I will be presenting results that include both the use of this model for interpolation applications, so basically for building gridded 4D products of dissolved oxygen nutrients. And it also being coupled to a physical model to run kind of coupled hybrid Physics-BGC based simulation. So this is a joint work. So I'm Saïd Ouala with IMT Atlantique in Brest, France, and this is a joint work with Zohair Lashkar, who is with the Arabian Center for Climate and Environmental Sciences in New York University, Abu Dhabi. So the motivation for this work is that we were interested in studying oxygen minimum zones, and for those that are not comfortable with these, oxygen minimum zones are regions in the ocean with very low oxygen concentration. So in some regions, it can be even very close to zero. And those objects, those oxygen minimum zones, are important for all sorts of things. They kind of shape the marine life and the marine ecosystems, and they're also responsible for some feedbacks within the carbon cycle. So we were interested in going beyond kind of statistical analysis and climatological distributions, and we wanted to study the time variability of oxygen minimum zones, and we wanted to study this time variability over different time scales ranging from seasonal to interannual and to more kind of larger time scales that are in relation to climate change. Now, the issue when we want to do this using observational data records is that there are substantial observational gaps in the existing observations of dissolved oxygen. It's even worse for nutrients. So what I'm showing here is the space-time sampling of dissolved oxygen observations from 1950 to 2023. And the observations here are aggregated over 5-year intervals. And the colors kind of indicate the maximum depth of the profile. So it's mainly red, meaning that the profiles go beyond 2000 meters, which is good. But still, there are lots of regions in the ocean with little to no observations. So when we want to use this kind of observations in order to study the time variability of dissolved oxygen or nutrients or things like oxygen minimum zones, we usually need to do things like optimal interpolation, and we want to do when we want to do optimal interpolation of this kind of observations with this space-time sampling, we usually need to aggregate more and more observations, which tends to smooth all the fine scale variability that we are interested in. So we cannot base our analysis only on dissolved oxygen observations. Another idea is to use numerical simulations. And there is this very nice work from Ito et al. 2024 that took a number of Earth system models that are able to, or that do have dissolved oxygen outputs, and they compare the dissolved oxygen simulations in the historical period to the one of the observations. And what they show is that most of the numerical model outputs simulations do not necessarily agree with historical observations with correlation coefficients that are close to zero. And another observation is that while the most of these Earth system models are able to simulate a loss in the oxygen content, which is shown here by a negative trend in the oxygen content, meaning that the ocean is losing oxygen in the historical period, which is what we expect, what was observed in observations. The issue is that most of those models do not, or all of those models do not agree on the rate at which the ocean is losing oxygen. Another issue, and it was pointed by other works, is that most of those numerical simulations are not able to accurately reproduce oxygen minimum zones in terms of their intensity and their volume, which are really the objects that we want to study. So we cannot use numerical simulations. And from here, the idea that we wanted to go through is to use better observational coverage that is present in hydrographic data networks. And we basically used physical observations, so basically temperature and salinity, because they present a much better spatiotemporal coverage, and particularly after the Argo era, after year 2000. And the idea here is to train a machine learning model in order to produce biogeochemical variables, so basically here dissolved oxygen nutrients. And then once this model is trained, the question was, can we use this in order to artificially increase the number of observations so that we can have a better space-time coverage of BGC variables so that we can do optimal interpolation? And the other question is, once this model is trained, can we couple it to a physical model in order to kind of diagnose BGC fields that are consistent with the simulated physical variability? So this slide is kind of to explain the general framework that we developed, that we are working on, and then we will go through each of these elements step by step. So the first step here was to do the in-situ data collection. This is quite standard, and I'm sure lots of you have already done this. Second step was to design the machine learning model. It's basically a neural network emulator. It's basically a neural network model per BGC variable with a coupling between oxygen and nutrient networks. I will go back on this in the next couple slides, but the idea of the second step is that to have these neural network models trained and validated so that we can use them both for graded um, products generation using optimal interpolation. And here we have two different products with two different resolution, and we'll explain why we have this. And the last step is to couple this, or the other application, I must say, is to couple this neural network emulator with a physical model in order to run coupled physics-BGC based simulations. So regarding the first step, regarding the institute data collection, this is, as I said, quite standard. So what we did is that we simply downloaded all the available data in World Ocean Database from 1965 to 2024. And the variables that we were interested in are basically temperature, salinity, oxygen, and nitrate, and also phosphate and silicate observations. The second step was to design what we call here a multi-stage quality control procedure so that we remove all the bad or outlier profiles. And this multi-stage QC was basically based, the first filter was to use the flags provided by World Ocean Database. So basically to keep all of the measurements and all of the profiles that were flagged as acceptable. And then we designed a number of quality control schemes based on the variables. So, for example, we removed all of the variables that had constant concentration for a certain number of depth levels. We also, so for dissolved oxygen, for instance, we removed measurements that were having some anomalous supersaturation levels beyond some predefined ocean depth level. And for the nutrients, what we found that was actually practical in terms of maximizing the good data retention rate, and also removing all of the bad profile, is actually to define a QC that is based on a thresholding, a local thresholding that is based on the world ocean, on a pointwise world ocean climatology plus minus a threshold. So all of the profiles that fall into this interval are kept, and all of the profiles that are out, other profiles are flagged as outliers and are removed from the study. And at the end, we ended with around 29 million quality control samples for dissolved oxygen. For nutrients, it's slightly less; it's around 90 millions. And we divide those samples into training, validation, and test regions. Now, regarding the neural network architecture, it's a simple multi-layer perceptron. The architecture is actually quite inspired from the work of Raphael Sauzet, which is present here, in her paper of 2017. And what we did here is to basically have two different models. A model for dissolved oxygen that takes as a prognostic variables, or as input variables, the physical variables of temperature and salinity, and also space-time variables, things like depth, latitude, and sinusoidal encoding for the month and longitude, take into account of the periodicity of these variables. And the nutrient networks also use, in addition to these variables, it also uses dissolved oxygen as an input. Now, this is what we do in training phase, but in inference phase, we want to be able to predict nutrients without having to use dissolved oxygen, so that we can augment the number of nutrient profiles, especially after the Argo era, where dissolved oxygen measurements are not necessarily available in the first year, so basically before the launch of BGC Argo. So what we did in the inference phase is that we coupled the dissolved oxygen network to the nutrients networks, so that dissolved oxygen model is able to produce a dissolved oxygen input to the nutrient network, so that we are able to predict nutrients everywhere we do have only temperature and salinity observations. And what is interesting about this kind of architecture when compared to another architecture, because we tested also another architecture that predicts nutrients only based on temperature and salinity. And what is interesting about this architecture is that it exhibits interesting bias compensation properties, especially when coupled to a physical model. So for when coupling this kind of architecture to a physical model and the physical model has a bias, the bias in the physics tends to cancel with the bias in the dissolved oxygen, leading to less sensitivity of the predicted nutrients to biases in the input physics, basically. So once the model is trained, we evaluated this model on a number of independent test regions. So these results are for dissolved oxygen, but we have exactly similar performance and similar metrics for nutrients networks. So what we did is that we defined a number of 23 independent test regions that are sampled all over the oceans. And the goal here is to sample different biogeochemical provinces so that we make sure that our model generalizes to different biogeochemical provinces. And the idea is that for all these independent test regions, we defined a 1 degree times 1 degree box, and all of the profiles that are inside of those 1 degree times 1 degree box are excluded from training and validation and are used only for evaluating the neural network model. And what we have here in the right is basically the averaged emulated profile by the neural network emulator when compared to the distribution of observations inside each of the 1 degree times 1 degree boxes of all the regions. And it shows that the model is basically able to capture quite well the different dynamics of dissolved oxygen variability all over the oceans. And this includes regions with very low oxygen concentrations around oxygen minimum zones in the Arabian Sea, such as those two test regions F and G, with oxygen concentrations close to zero. And it also includes very highly oxygenated regions in the higher latitudes, for example. And yeah, and we also, one thing that came up, and this came up actually after review, what we also saw is that this neural network model was actually quite robust to the presence of outlier in actual wood observations. So for example, in this G test region, there were some outliers in the wood dissolved oxygen observations that somehow skipped went through the quality control procedure. And what we were able to show is that even with some outliers existing in the training set and also the evaluation, the neural network model, due to its continuity, is able to kind of mitigate some of this anomalous behavior, which kind of suggests that this kind of model can also be used to things like anomaly detection, for example. Then once we have trained those models for dissolved oxygen nutrients, and what we did is that we started the first application, which is basically the optimal interpolation of all the dissolved oxygen measurements coupled to the emulated dissolved oxygen measurements. And what we did here is that we defined two different products, one with a yearly resolution from 1965 to 2024, and one with a monthly resolution from 2005 and 2024. And what I'm showing here is the sampling of the dissolved oxygen measurements of both products, where we do include the emulated observations by using the neural network. And as we can see, after the year 2000, we have a huge increase of, due to the launch of the Argo program, lots of temperature salinity profiles that are converted here into dissolved oxygen nutrient profiles, which basically suggests the refinement of the product with building this new product with a better resolution after the year 2005, basically. So once we did the optimal interpolation, the first evaluation was basically to evaluate the climatology of our product as compared to World Ocean Atlas, for example. And this is what we are showing here. And we were able to reconstruct quite well both the horizontal climatology and also the vertical distribution of the ocean dissolved oxygen in regions that do include oxygen minimum zones. So for an instance, we were able to reproduce quite well the both the intensity and the volume of the oxygen minimum zones in the Indian, Pacific, and the Atlantic Oceans. And a second step was to try to evaluate the gain that we have in our models in terms of number of observations and their impact on the uncertainty of the product. So what we are showing here in the left is basically the number of profiles per year or number of observations per year used in optimal interpolation. We have in orange the only the dissolved oxygen measurements. And in blue, we have the emulated observation. So basically, it's a proxy of temperature and salinity. And what we are showing is that we increased the number of observations used in interpolation, in optimal interpolation by roughly an order of magnitude. And what this translates to in terms of the yearly product, and it's shown here in the right, is that with this huge number of additional observations, we are able to reduce quite significantly the uncertainty of the reconstruction. And it can be seen here in those two panels where we show in the above panel the standard deviation of the dissolved oxygen product at year 2025 at 200 meters. And green dots here represent the sampling of dissolved oxygen observations, because this product only used dissolved oxygen observation, not use emulated data. And what optimal interpolation does basically is that for every pixel where there are lots of neighboring observations, it will give it a small uncertainty because it will reduce the uncertainty of the background. But for the pixels with little to no observations, there will not be a huge correction, so we will only use here the uncertainty of the background field. And it's here for poorly sampled regions in the product without emulated profiles, it's roughly something around the standard deviation of 5 micromole per kilograms, which is very big in oxygen minimum zone regions, because in those regions the oxygen concentrations is around zero. So this is an issue, and we do mitigate this in our product by using emulated data, because now we are able to sample quite well all of the ocean, which results in a reduction, a significant reduction in the uncertainty of all the interpolated product, basically. We then a second step was to try to evaluate the trend of the oxygen content reconstructed by our product, and to compare it to earlier studies that are based on pure observations, so only dissolved oxygen observations, and similar statistical mapping methods. We compared here our work to Schmidt-Co et al. And to also the work of Ito that is based on only dissolved oxygen measurements. And to be completely honest, we were a little bit scared about this step, because we know that most of the there is an order of magnitude more emulated observations than real observations. So we were scared that with a drift in the emulated observation, we will get some deoxygenation rates that would be irrealistic or things like that. So we were very rigorous or we very severe with the we kind of designed another quality control step, and I will not get into the details, to filter emulated profiles that are irrealistic in some metrics. And by doing this prior to optimal interpolation, we were able to reconstruct a dissolved oxygen product that simulate the oxygenation rates that are in agreement, or at least on the same order of magnitude than ones of previous studies that are only based on observations. And in the second phase, we also did a little bit of a qualitative comparison of our product to more recent reconstructions that are based on machine learning. So here in green, we have the new reconstruction of Ito et al. That uses machine learning, and also the Go by product by John. And what we are showing here is basically the oxygen content per year. And what we uh, what we um, what we observed is that we are on the same level in terms of oxygen content and also in terms of oxygenation, in terms of deoxygenation. But what was revealed by our product and what was interesting to us is that there were some kind of shift in terms of the oxygenation dynamics, meaning that we identified that there were some different oxygenation phases with the deoxygenation alternating between a slow deoxygenation in the first kind of 2 decades of the product, then a fast deoxygenation phase in the years from 1980 to around 2000, and then followed by slow deoxygenation phase in the last 2 decades. And when Zuhair, my collaborator, looked at this, he told me that yeah, this is kind of a um, um, in phase or highly correlated to the PDO, to the Pacific Decadal Oscillation phase. So when the Pacific Decadal Oscillation is positive or has a positive phase, we have a faster deoxygenation. And this was actually something that was documented and studied in some earlier work, so particularly the work of Poupon et al., that used numerical simulation in order to study this link between faster deoxygenation and PDO phases. And our work was able to reproduce this kind of coupling using observations. So in current studies, we are trying to dig a little bit deeper into this link between Pacific decadal oscillation and deoxygenation dynamics. So what we did in this recent work, and it's submitted to geophysical research letters, what we did is that we took the ocean oxygen content simulated by our product, and we deseasonalized. We took off the seasonality and the trend, and we focused on the interannual variability of the product. And what we are showing, we can focus on the upper left figure. We have here in blue the oxygen inventory, so the oxygen content simulated by our product. We have in dashed lines the smooth PDO index. And in red, we have the oxygen minimum zone volume. So it's basically the volume of ocean with a concentration of oxygen that is smaller than some predefined threshold, basically. And what we were able to show in this work is that the ocean oxygenation or deoxygenation is not linked, is not correlated actually to the PDO phase, but it's correlated to the PDO rate, meaning that the oxygen is gaining the interannual variability of oxygen is basically increasing when moving from a negative to a positive PDO phase. And inversely, the ocean is losing oxygen when moving from a positive to a negative PDO phase. And inversely to this, what we showed is that it's the oxygen minimum zone volume that is actually correlated to the PDO state itself, with basically uh, lower or an increase in the oxygen minimum zone volume that is corresponding to a positive Pacific decadal oscillation phase, and a decrease in the oxygen minimum zone volume or the interannual variability of the oxygen minimum zone volume that corresponds to a negative PDO phase, basically. Another study is we are also trying to kind of study the internal composition of oxygen minimum zones when smoothing the interannual variability and focusing on the signal in the first 2 decades versus the ocean oxygen minimum zone composition in the last 2 decades. So what we did here is that we plotted basically the volume histogram of the oxygen minimum zones for different oxygen minimum zones. For example, if we focus on the Arabian Sea, we have here in the x-axis it's oxygen bins. And in the y-axis, it's the volume of oxygen that falls in these bins, basically a volume distribution. And what we were able to show is that for oxygen minimum zones that are dominated by suboxic conditions. So basically the intense oxygen minimum zones that do have a suboxic core. So basically the core of the oxygen minimum zone is with a concentration that is very small. So basically smaller than things like 10 to 5 micromole per kilo. So for those very intense oxygen minimum zones in the Arabian Sea and Bay of Bengal, for example, the ones in this upper panel, we have when we compare the volume distribution in the first 2 decades to the volume distribution in the last 2 decades, we have an increase in the suboxic core, but a decrease of the volume of water that are between the suboxic and hypoxic core. But when we compare, when we do the same analysis for the oxygen minimum zones that are weaker or that do not have a suboxic core, what we observed using this product is that we only have an increase on expansion of the hypoxic volume of oxygen minimum zones. Meaning that this product suggests that the variability of oxygen minimum zones or the long-term variability of oxygen minimum zones when comparing the first 2 decades of the product to the last 2 decades actually depends on the intensity of the oxygen minimum zones. Now to the last part of this talk on the coupling of Neural-BGC with the physical model. So what we did here was we coupled the emulators that we trained previously without any fine-tuning and without any retraining to a physical model. And we used here the regional ocean modeling system, ROMS. And we focused on two particular test regions, the Arabian Sea and the Canary current upwelling systems. And we focused on these two regions due to two main reasons. The first reason is that they are interesting from a biogeochemical point of view, because in the Arabian Sea, we have a very intense OMZ, and we're interested if we're able to reproduce it using a coupled hybrid Physics-BGC model. And in the Canary system, there is a strong upwelling of nutrients, and we're also interested in seeing whether we were able to reproduce this variability. And the second reason why we choose these two regions is that there were some studies that already kind of established a standard coupled ROMS NPZD model for modeling the biogeochemistry using NPZD model. So it's already two regions for which we already have a baseline to compare our Neural-BGC or hybrid Neural-BGC model to. So the first comparison targeted the comparison of the seasonal cycle. We have here in the upper panel dissolved oxygen seasonal cycle, and then in the lower panel we have the NITRAT, and in the left we have Arabian Sea, and in the right is a Canary upwelling system simulation. And the emulator was able to reproduce quite well the seasonal cycle. There is no real challenge in reproducing the seasonal cycle, which is good. And the second evaluation was to see whether the hybrid coupled ROMS Neural-BGC model was able to reproduce things like nutrient blooms and intense oxygen minimum zones in both the Arabian Sea and also in the Canary upwelling system. So in the Arabian Sea, we compared the climatological distribution of the observations, so taken from World Ocean Atlas, to the standard ROMS NPZD simulation, and to the hybrid ROMS Neural-BGC model. And so in the left, we have dissolved oxygen, and the horizontal layer here is taken at 200-meter depth so that we can evaluate the oxygen minimum zone. And in the NITRAT, we are plotting at the surface so that we can see if there is some nutrient blooms around the Gulf of Aden, for example. And maybe regarding the positive things about this model is that we were able to correct some of the biases in the ROMS NPZD model. So, for example, there is this big front of highly oxygenated waters around the equator, which is not realistic and not present in the observations, and we were able to correct it in the hybrid model. And we were also able to simulate a good nutrient bloom when compared to the observations with the hybrid models, but we were not able to simulate the correct oxygen minimum zones. We didn't get the volume of the OMZ right, and even the intensity was good, but not as intense as the one simulated by ROMS and PZD and also in the observations. Now, when we move to the canary appealing system simulation, there was kind of another picture because in the canary we were able actually to reproduce a quite intense and a quite better oxygen minimum zones when compared to ROMS and PZD. And we were also able to reproduce the canary upwelling of nutrients using the ROM's Neural-BGC model. So from here, we were kind of skeptical. I mean, the model was working quite well with, is working quite well with the canary in the canary simulation configuration, but has some issues simulating the oxygen minimum zones in the intense OMZ in the Arabian Sea. So we had some kind of hypotheses regarding maybe the sampling of the observations, because we know that there are less observations in the Indian Ocean, particularly around the past, the like around the years the 1990. So maybe the model performance was were due to the emulator not learning quite well in the Arabian Sea as it learned in the Canaries, but it actually was due to something else. And so in order to identify the source of these biases in the coupled ROMs Neural-BGC model, what we did is that we plotted the dissolved oxygen biases of both the standard NPZD model in blue. So this is the bias with respect to World Ocean Atlas. So I'm plotting here, it's basically the difference between the observations and the simulations averaged. And in blue, we have the bias of the standard NPZD model. In green, we have the bias of the Neural-BGC model. And in red, we have the bias of the temperature, of the simulated temperature. So basically, the physics that is driving our Neural-BGC model. And if we compare the Indian Ocean simulation and the Canary simulation, what happens is that in the surface, or in the upper ocean layers down to 2000 meters, the Neural-BGC model is actually doing quite well, and it's actually in the deeper ocean layers where Neural-BGC start to developing some kind of serious bias in simulated dissolved oxygen. And this was actually due to the fact that we had a bias in the simulated temperature that is on the order of 2 degrees, which is kind of a big bias that results in a bias in the simulated biogeochemistry or dissolved oxygen, because we will see that it's not the case for nutrients, and we'll explain why. But there is but the NPZD model was quite robust to this bias in the physics, which suggests that there is some bias compensation properties between the parameterization of the NPZD model and the parameterization of the physical model that allows to compensate kind of for the bias in the physics, basically, which is something that we can do on the dissolved oxygen, because we predict dissolved oxygen only based on physics, and we trained on observations. So if we are biased with respect to observation, we'll have a bias with respect to. So if our simulation is biased with respect to observation, we'll have a bias in the dissolved oxygen simulations. And this was confirmed in the Canary simulation, because in the Canary simulation, the green, which is the bias of the hybrid Neural-BGC model, is always kind of outperforms the bias of the NPZD model. And this is mainly due to the fact that we have a very small bias in the physics to start with, meaning that we are in a regime that allows our hybrid model to perform very well and to reduce the bias of the simulated dissolved oxygen. Now, one last note on biases is that all this bias analysis was correct for dissolved oxygen, but it was not correct for nutrients, because for nutrients, even though we have a bias in the driving physics, we don't result into that much of a big bias in the simulated nutrients. And this is due to the fact that we have some some tests that suggest this, but this is due to the fact that the cascaded architecture we discussed in the beginning, the fact that we are using the simulated dissolved oxygen as an input to the nutrient networks, actually give some kind of bias compensation properties, because if the physics is biased, then the dissolved oxygen is also biased, and those two biased at the input of the nutrient networks basically cancel out, leading to a smaller bias when compared to the dissolved oxygen. I will conclude now my presentation. So we developed a dissolved oxygen nutrient emulator based on machine learning using in situ temperature and salinity profiles to expand data coverage. And the model is used both interpolation and simulation applications, and shows accurate results when compared to state-of-the-art, both graded products that are based on only dissolved oxygen measurements, and also that are based, more recent ones that are based on machine learning also. And it also shows accurate results in terms of simulations when compared to well-calibrated coupled ROMs and PZD models. And future works are targeting right now the interpolation of other BGC variables. So basically, we are working on nutrients. We basically to produce a graded nutrients product. We also the nutrients were actually quite harder because uh, the data are sparser and they are more. There are. We felt that there were more outliers that we cannot target easily. So we designed kind of ideas and tricks in order to get a clean data set. There was also an issue in constructing the background field of nutrients in order to do optimal interpolation. So we spent some time doing this, but now actually the nutrients products is ready, and we are kind of analyzing the outputs in order to publish the work. And we are also working in using the Neural-BGC as an emulator in projection applications. So we're collaborating with a team from Météo France that are building a regional climate model for a particular anthropogenic forcing emission scenario, and we are collaborating in order to provide Neural-BGC in order to simulate also biogeochemistry and see whether how it generalizes to different forcing scenarios and things like that. So these are differences, and I will be happy to take questions or to discuss whatever you want to discuss. Thank you very much.
Thank you, Said.
Welcome.
Thank you very much for this nice talk. Do we have any question from the audience?
I have a question if it's okay to just jump in.
Yeah, of course.
Hi, thanks for the great talk. I'm
Hi,
just
thank you.
curious. I'm curious about so applying kind of these different layers of machine learning, so doing the nitrate predictions on top of oxygen predictions, and what your thoughts are on how, and then the temperature salinity product that you're predicting on is itself a gridded product, right? So I'm wondering about your thoughts on scale compression during these various steps of gridding and interpolation.
So basically, what we thank you very much for the question. What we don't predict nutrients and oxygen based on gridded products. Actually, we predict nutrients and oxygen using in situ observations and not interpolated ones. So these provide us with a better, let's say, coverage of dissolved oxygen and nutrients. And then after this, we use all these observations or profiles, so both dissolved oxygen profiles that are actually measured and the ones emulated from temperature and salinity profiles to do optimal interpolation. So we don't predict, if I get your question correctly, we don't predict dissolved oxygen and nutrients using or a gridded product. We predict them directly from the actual profiles, basically. And it's after that we increase the space-time coverage using those profiles, and it's after that we do interpolation.
Thanks.
You're welcome.
Any other question? Yeah.
Hi, everyone. Hi, Said. Thanks.
Hi, Ariana.
This was a very interesting presentation. I have a question about the strength relationship that you found between deoxygenation and PDO. Did you only look at global deoxygenation trends, or did you also look at regional decomposition? And in that case, did you see contrasting signals between different basins and anything like that?
So thank you for the question. So for this here, it was global. So both for the Odo inventory and also the volume of the oxygen minimum zones, we did this globally. But there were contrasting signals when looking at different basins, especially when doing this analysis regionally or different oxygen minimum zones. We tend to get the same results but shifted, basically.
Thank you.
You're welcome. We have a paper. It's still a preprint, so it's under review, but you can take a look at what we did there.
I can jump in with one. Thanks,
Go
Saeed.
ahead. You're welcome.
So you had a figure that showed the global trend compared with Taka's recent product and the Go By. Yeah. I think something that we've seen in our GoDip oxygen mapping group is that sort of toward the end of the time series with Argo data included, there can be somewhat of an acceleration in the trend, so kind of faster deoxygenation in recent years, and we've associated that with kind of a slight negative bias in some of the Argo measurements compared to shipboard oxygen measurements. But you see kind of a slowing down toward the end of the time series. I didn't catch if you were doing any sort of adjustments to Argo oxygen measurements or if you had any thoughts about that kind of tailing off of the deoxygenation.
Yeah, thank you, John, for the question. So we didn't do any bias correction to Argo. And one thing that it's worth to look at is maybe to see whether th- this slower deoxygenation is also something that can be seen in other products. Is that here we are only evaluating the yearly product basically. So there is a lot of smoothing going on. Because we basically, to interpolate a single pixel, we use all the observations from plus there is a 5-year averaging going on. So I'm wondering if but it will not explain the fact that you are seeing a faster deoxygenation toward the end. So maybe it's a method artifact, basically. I'm not really sure. So I would say it may be a method artifact. So there is something to evaluate here. But for us, we were kind of confident because it kind of validated the hypotheses there were in the literature regarding this link between PDO and deoxygenation. So for us, it was something that is consistent from this point of view, but there is definitely something to investigate between these different products and maybe the way we do interpolation, because we have slightly different methods, and maybe this would explain the differences in your interpolation and ours.
Yes, Taka?
I said great
Hi,
work.
Taka. Thank you.
So one question I had was about the OMZ definition. I was wondering what threshold of oxygen you use to define the OMZ volume, because if you use relatively high value like 80,
So
then
here,
the trend you see
right.
is mostly coming from. Go ahead.
Sorry, I didn't catch the last part of your sentence, but I
Oh,
can
yeah, I
talk
was
it.
just
Yeah.
Yeah, I was just wondering what the threshold were and how close you were to the core of the onesie.
Yeah, so basically here, so for this study here, the OMZ volume is defined um, based on it's global. So basically, the threshold is different whether we are in an intense oxygen minimum zone or we are in a weaker ones, for example, in the Atlantic. So s- in intense ones, so for example, in the Bay of Bengal and in the Arabian Sea, we use the threshold of 20 micromoles per kilo, something
Mm.
around 20. And in weaker ones, we increase the threshold so that we take into account the ones in under the Atlantic, basically.
All right, thank you.
Yes, Zankun?
Yeah, very nice presentation. So I'm glad to see that you used the World Ocean Atlas to compare the result. I work for NOAA and we developed the World Ocean Atlas. My question is, for Argo oxygen, we applied a bias correction when we develop the World Ocean Atlas. So you said you didn't apply any bias correction. So that might explain some of the differences you see in your simulation. Keep that in mind because we do find that there's a bias about 1.7 millimole per kilogram in the Argo oxygen data. I have a paper on that. I can share that with you.
Yeah, thank you. Thank you, Zenkun, for the comment. We were unfortunately, due to my ignorance, I was unfortunately aware of this bias too late. But it's interesting to maybe take it into account or its impact into the simulations, especially when coupled to a physical model, or its impact on having like biases in the physics also. So. Uh,
Yeah.
But then regarding that, when we compare things like climatological distributions and also deoxygenation trends, I don't know, but we didn't feel that we were quite different. But this may be bad because this is based on statistical mapping estimates that only use dissolved oxygen observations. So maybe it's not a ground truth, basically. It doesn't mean anything, but yeah.
Right. Yeah. So my another question is, you used the in situ temperature and salinity to produce to expand the dissolved oxygen
Mm.
profiles. So do you use the predicted and the real in situ observations equally, or
Yeah.
you weighted
Yeah. Thank
okay.
you. Thank you. Yeah, so we use both. We use both in optimal interpolation, and we kind of weight differently the dissolved oxygen measurements. We give them a higher weight than the emulated ones through basically the measurement noise, because when you do optimal interpolation, you need to define this signal to noise ratio, and basically it's better for observations than for emulated ones.
Oh, okay. Yeah. Thank you.
You're welcome.
Any other question? Okay. So thank you again, Said, for your nice talk and the discussion after.
Yeah, thank you. Thank you for the invitation, and I hope let's keep in touch. I hope that I will be present in other webinars, I hope.
Yeah. And thank you everyone to have connected to this webinar.